So what are, now let's start talking about, now that we understand the importance of RAID, now that we understand what is RAID, what does it do, what's the purpose of that. Now let's talk about, so basically what are the details or how do we design RAID? What are these different RAID algorithms or mechanisms like RAID 0, RAID 1? How do we do the trade-off, the questions that we earlier in the first page of this lecture we discussed. So what are the important aspects of RAID? First, interface. So this piece of miniature computer system called as RAID should allow us an interface Word and any other disk would also allow. So we should keep all those interface calls that we discussed about, that we should be able to open the file, read the file, write the file, and this file system that does all those things should be able to work with the block IO layer, and that block IO layer should be somehow able to work with this, with our storage device. And now if instead of storage, a single storage device, instead of that, if we have a RAID that internally has multiple storage devices, but somehow it this RAIDs, like the system interacts with all the upper layer of the system, then we should be able to respond in the same way as possible as we would have done with a single disk as well. Second, it should have a particular fault model, right? The whole purpose of designing RAID mechanisms is we want to achieve fault tolerance. If fault happens, then how can we recover data after the fault has happened or after we have lost a disk, something like that. So it should have a particular fault model or a plan. And third, now, once we have a RAID mechanism, we would want to see how good is this RAID mechanism, right? Like, is this just survivable? Is this just okay? Is this the best RAID technique? Something like that. So how to evaluate? RAID design. Now, definitely, as soon as I talk about how to evaluate, because we already discussed the 3 important parameters that matters to any storage device. So you should be already thinking that, well, that's easy. How to evaluate, we already know. Evaluate the performance, evaluate the reliability, and evaluate the capacity that this RAID is able to provide. Yes, you are correct. That's exactly the parameters that matters to us while we evaluate the RAID. So then let's talk about the interface and RAID internals. So as we just discussed, to file system, RAID look like a disk. It cannot differentiate if it's a single disk or it's a RAID mechanism underneath. It presents self as linear array of blocks, each of which can be read or written by a file system. So one logical IO, which is an IO issued by the file system, can be multiple physical IOs inside RAID. Depending upon what algorithm are we using. And now looking at this or reading this, you may be already thinking that yes, it does make sense because somehow this RAID, which consists of multiple physical disks, is able to provide a mechanism in which one of the disks could fail and one or more disks could fail. And if we want to do that, then we would have to store, like, there is no magic in a way that we would be able to make that failed disk work again. If that disk has failed, if it has failed truly, then it has failed. We have lost the data inside that. So somewhere we should have like another copy of this data on some another disk, which this RAID as a whole box should be able to fetch the data from. So yes, it makes sense that logically, if there is a single IO from file system to the RAID box, then internally inside the RAID box, that could result into multiple IOs, such as the same data stored across two disks. So one of that, if that fails, then at least we'll be able to get the data from the other copy that we have. So that makes us visualize the RAID box as something like it has this multiple disk inside it. File system performs logical IO onto this. Now this logical IO can be translated to multiple physical IOs inside. So one logical IO may lead to two physical IOs if we have two disks. And this mechanism of exactly mirroring the same data across two disks, it is what it's called as RAID 1, which is mirrored technology. Very simple, right? Very straightforward, but very useful. RAID mechanisms are one of the highest used fault tolerance mechanisms even today. So these are just very simple, basic ideas, but still very useful, very impactful ideas that has made a big footmark in the world of storage systems, and these ideas are being used. We'll discuss more about RAID 1 in detail soon. Second parameter that we mentioned after interface and RAID internal was fault model. So let's first just take an overview of fault models. So RAIDs are designed to detect and recover from certain faults. And what are these certain faults? Basically, in terms of storage device, the worst fault would be losing the storage device itself, losing all the data on the storage device, or losing a part of data on any storage device. So this, when we say fault, we mean, well, we lost some data. We don't bother about how we lost it, but we lost it. Now what do we do? Thus, knowing exactly which fault to expect is critical in arriving upon a design that would work the best, right? Knowing, okay, what type of faults can we have in a system and what type of faults do we want to care about while we are designing this RAID mechanism, such as RAID 0, RAID 1, etc. That will give us more intuition on exactly how we can design these mechanisms well, right? If anything is worth if anything is worth the work, then it's better worth to do it right? So if it's worth to design an algorithm, it's better to spend efforts to design this algorithm such that it serves the purpose in the most efficient way it can. So this fault models, let's learn about what type of fault models do we have and what types can we tackle by designing or what types are we bothered to care about while we think about designing RAID algorithms. So one of the fault model is fail-stop model. What is fail-stop model? So what fail-stop model says us is the disk can be in exactly one of the two states. That's either working fine, so nothing's wrong with that, or totally failed. So either all the data on the disk is fine, or all the data on the disk cannot be accessed. This is what exactly is called as fail-stop model. So on a working disk, all the blocks could be read and written. And on a failed disk is the disk on which the data is permanently lost. Now, there is a little caveat here, which might already be bothering you, is when we say that the disk is failed, now we are not, let's assume that this is easily detected, because in practical environment, sometimes a disk could be failed, but also detecting that the disk is failed or not, that's a challenging task. But we cannot deal with the failure until we know that it's the failure, right? So when we are talking about that, talking about the fail stop model, and when we say that the disk is failed, let's have this assumption that we could easily detect when the disk fails, and we have some mechanism already in place to do that. So for example, the rate controller, which could be hardware or software, right? There are different types of rate controllers. Can immediately observe when a disk has failed. So there is some mechanism already set in place which could report to the rate controller, so that rate controller could immediately observe as soon as the disk that it's managing, one of that disk fails. There's no worries about silent failures such as disk corruption, where a disk could get eroded over a time, or could catch some moisture, or could stop rotating or something like that. So where disk is still working, but not working in a way we expect it to work. So we do not worry about those silent failures. And we also do not worry about the partial failures, like some blocks in the disk could be read and some other blocks could not be read. So things that we do not worry about. Silent failures. So these are the scenarios where a disk is failed, but RAID controller doesn't know that it's failed. Let's not worry about them right now. And second type of failures, such as partial failures. So where certain portion of the disk is failed, but still there is certain portion of the data on that disk that still could be read perfectly fine. So in order to deal with that, we could definitely have different modifications to the RAID algorithms that we are discussing, or maybe some of them we could use as it is to deal with partial failures, just to recover certain blocks of data and not the entire disk. But to keep it easy, let's not worry about these scenarios as of now while we understand the basics of RAID algorithms and discuss that. Now, if this discussion of silent failures and partial failures have already triggered thoughts of, oh, what are the other types of failures in your mind, then keep those horses running. It never hurts to think about different possible scenarios, right? You could frame examples in the sense that what are the other types of things that could go wrong? And you might come across some other terminologies like intermittent failures or permanent failures or something like that. But there could be different hardware reasons or different reasons behind each of these types of failure. For example, one of the research article, popular research article reported that most of the time when a storage system is not performing as we expect it to, then the reason is loose connections. It's just the bus through which this hard disk are connected to the server that gets loosened over a time, because hard disks is a physical drive. So they have a lot of physical movement inside that, which could lead to some vibrations. And that minute vibrations could loosen the connection. And because of these loosened connections, now we do not get as much bandwidth as we expect from this hard disk, or as we got initially. So sometimes the reason for failure may even not be inside the hard disk, but still that's the reason for failure. Let's keep thinking about that, but let's not worry about all these transient failures, partial failures, silent failures today while we discuss about these RAID mechanisms. So now that brings us to our third aspect that's important to us, which is how to evaluate a RAID. So there are many different approaches to build a RAID, as we would see some of the naive RAID algorithms in this lecture. And each of these version of RAID mechanism could have its own strength or weakness. As we have learned in systems area as of now, every problem can be solved, but the solution might give rise to new problems, right? So every RAID algorithm could have some strengths, some weakness, and it becomes interesting to compare that. So what are the axes over which we could compare these strengths and weakness? As you already know from what we discussed until now, capacity, reliability, and performance are our three big weapons to compare this. So capacity, how do we compare the capacity? Let's say that given n disks with B blocks each, how much useful capacity is available. That's what we could measure on this axis of capacity. So if we have one n block n, if we have one disk with B block, the total capacity we have is B. If we have two disks with B blocks, then the total capacity we have is 2B. Now, the physical capacity that we have is 2B, but what is the useful capacity? Like, what is the capacity that RAID as a box exposes to the file system? That's the useful capacity that we are talking about here. Is that still 2B or is that just B? That's how we would get an idea about how good is this RAID mechanism on the capacity axis. Second, reliability. Which is a measure of how many disks, failures, or disk faults can the given design tolerate. So now from what we discussed about the false, fail, stop, false, and the assumption that we are carrying forward is that the whole disk would fail entirely. So a disk is either in two state, either working entirely fine or having a fault. It's like 0 or 1. If we are having such disk which could fail, then to measure how this RAID is doing over and how this RAID is performing, or what is the reliability of this RAID, to measure that, a very important thing that we could look at is how many disk failures or disk faults can this RAID algorithm tolerate. Let's say if I have 2 disks and 1 out of that failed, is that fine with this RAID? Okay, then it can tolerate 1 disk failure. But if I have 2 disks and both of them failed, is that fine with this RAID? I think it would be great to have such a RAID algorithm, right? Well, maybe you can invent something like that if it's possible. I don't know. But that's exactly what we evaluate on the metric of reliability. Third, performance. Here, what we are seeing is evaluating performance is quite challenging because how we define if this RAID is performing good or not. There is no binary metric like that. There is no clear division. So in order to compare the performance, to evaluate, it depends on other parameters. And when we say it depends on other parameters, one of the key parameter there is the workload itself, right? If the workload is not performing enough number of IOs, then definitely any storage device or a RAID box would not perform well because there is just less workload on that. So if there is a less workload, you can't blame it to do less work, right? If the course does not give you an assignment, then we cannot blame you not to do an assignment because the assignment was not given. So it's something like that. So as it depends, heavily on the workload, presented to disk. So we cannot, in general, we cannot just say if this is performing good or bad. That would be very vague or very tough to identify, very challenging. But what we could do is we could discuss how would this perform with some typical workload. Like, let's say if we have an idea of the workload, if the workload is this, now say me how would this rate technique 1 would perform compared to rate technique 2 on this given workload. That is what we could do, right? So we will discuss the performance with some typical workload.